Let us have a look at the first menu item. It takes us to the Material Data, Rheological Plots, and Calculator submenu. This submenu provides you with all the tools you need to create and manage your material database and use it for the prediction of different rheological parameters. The first item here is Manage Material Data. Using this, you create, view, edit, and maintain your material database. Once you have created your database, you can then use the second, third, and fourth menu item functions to generate different rheological plots. You can also calculate viscosity and shear stress at different flow conditions using the viscosity calculator, which is the fifth menu function. Let us select the first submenu item, Manage Material Data. This takes us to the Material Data Management screen of this app. The first function is View or Edit Database. Since we haven't created the database yet, selecting this function will tell us that our database is empty. So we come back to create our database for the first time. We can start by adding a new material to the database, but it would be an idea to first try the examples that are provided within this app and look at their data card and explore how they behave rheologically. So we press Load Examples. We get a message that the app has loaded 8 inbuilt examples. Let us have a look at these examples now. We are now ready to have a look at our material database. As we press View, it opens a list containing all the materials that are currently in the database. We can see the 8 examples that we just loaded. We select the first material, chocolate. This is the material data card for our chocolate. We see that its flow behavior follows the Casson model. The Casson model is a yield stress model used to describe the flow behavior of many yield stress materials, especially in food rheology such as chocolate. This is a 2-parameter model with tau 0 as the yield stress, which in this case is 21 Pascal, and the Casson viscosity eta C of 3 Pascal second, which is its viscosity at high shear rates. We also record the reference temperature Tref, which is the temperature at which the flow parameters tau 0 and eta C were evaluated. Next we look at honey. In the data card for honey, we can see that it has been classified as a Newtonian WLF material. It is Newtonian, so its viscosity will not change with shear rate. However, the WLF designation will provide the temperature dependence of its viscosity. So we can later use the temperature plot function to look at how viscosity of honey changes with temperature. In the material data card for honey, we first have eta at Tref, which is its viscosity at the reference temperature. We also have C1 and C2, which are the 2 WLF parameters which are required to calculate the temperature dependence of viscosity. Finally, we have T lower and T upper, which gives a temperature range within which the viscosity of this material can be measured. For liquids, you can set T lower to its freezing point and T upper to its boiling point. For polymers, you can use the melting point or the Tg as T lower and the maximum processing temperature or the degradation temperature as T upper. Our next example is polypropylene. Polypropylene is classified as cross-Arrhenius thermoplastic. It means that at a given temperature, it follows the cross model, that is, it has got a 0 shear viscosity, eta 0, at low shear rates, and a shear thinning index, N, at high shear rates, with an onset of shear thinning behavior at a critical stress, tau star. The Arrhenius designation tells us that we know its flow activation energy, EA, and so we can also calculate its shear viscosity at any other temperatures. Finally, the thermoplastic designation signifies that we know the pressure sensitivity of its viscosity, which is described by the parameter beta. However, as polypropylene is a semi-crystalline material, we can expect that this pressure sensitivity will not be very significant as compared to an amorphous plastic. Our last example is polystyrene. It is classified here as cross-WLF thermoplastic. Its data card shows the set of parameters that are very familiar with those who carry out injection molding simulations using CAE tools. The data card includes the 7 cross-WLF parameters, including the D3 parameter, which gives the pressure dependence of the polymers Tg. In a high-pressure, high-shear processing condition of an amorphous polymer melt, such as in injection molding operations, you can use this cross-WLF thermoplastic classification for your material to predict its pressure-sensitive viscosity behavior. As we have gone through the inbuilt examples, we are now ready to add our own material to the database. As we press the button Add New Material, it takes us to the screen where we enter the material parameters. The first entry is material name. Here we enter a unique name for our material. In this example, let us give it the name My Polymer Solution. Next, we select an appropriate flow behavior model for our material. Since we know that our polymer solution at rest has a zero shear viscosity of 0.3 pascal second at 25 degrees Celsius and becomes shear thinning at higher shear rates with a shear thinning index of 0.5, with the onset of shear thinning at a critical stress tau star of 10 pascal, let us choose the cross-Arrhenius model for its flow behavior. We chose the Arrhenius designation for our material because we also know the flow activation energy of our polymer solution, which is 30 kJ per mole. Finally, we enter the lower and the upper temperature limits, that is the range within which the polymer solution viscosity is measurable. Once we have entered all the parameters, we press Add. The pop-up tells us that our material data has been saved in the database. Please note that in the free version of this app, we can save maximum one material at a time. In the Pro version, you can store unlimited number of materials and create a large database, which you can also share with your colleagues as a text file.